Hello, welcome to my channel. Welcome to Rehandran. So today I'm gonna talk about source-free RC circuit analysis. So in the previous video, I talked about source-free RL circuit analysis. Source-free in time domain, we got the response I t equals for initial current in the inductor we got IO e to the power minus t r by L. This was the circuit response, the loop current, you may say IT. And in frequency domain, after analyzing the circuit in frequency domain, we also got the same answer. IT equals IO to the power minus t r by L. So this was the result for source-free RL circuit. Now we are gonna analyze the source-free RC circuit in time and frequency domain and see what is the answer. For source-free RC circuit analysis, let us first draw the circuit here. So R and C. So this is a source-free circuit, and uh, we know that capacitor and inductor are dependent of frequency. Capacitors and inductors are frequency dependent circuit elements, and they store energy. Inductors store energy in terms of DC current, and capacitor stores energy in terms of voltage. And so let us assume that capacitor has initial voltage in it, which is VO equals V0 minus equals V0 plus. Okay, so this is the full expression for initial voltage across capacitor. So now to analyze in time domain, so time domain analysis, time domain analysis. RC circuit is an LTI system, so it will generate linear differential equation with constant coefficient. So let us apply this is also linear circuit, obviously linear LTI system. So as RC circuit is an LTI system, it abides by superposition principle. Due to superposition principle, we can apply KVL KCL. So for RC source free circuit, we will apply KCL. For convenience, you can also use KVL. So by KCL, so by KCL now, by applying KCL, we find at node assume node voltage is VT. Node voltage. The equation gives for current IC, IC plus IR equals to 0, because there's no source. The circuit is source free, and the current is obviously in the same direction. Or we can also write this in this form: IC equals minus IR, which is also uh, a, um, a relationship, a valid relationship, IR. Okay, so This is because by convention it becomes IC plus IR equals 0. Okay, and the two are equal and opposite. The current across a resistor and current across capacitor are equal and opposite to each other. By we have assumed it that way, and as there's no source, the two when the two when summed, they equal to 0. So uh, now let us rearrange the equation. The equation by rearranging gives IC plus IR equals 0, which gives we know that IC is current across capacitor is DC dV, which is function of T dt, plus VT, who is G node voltage, by R equals 0. Now now say d by dt is differential linear operator in this case, which will give CD plus 1 by R V t equals 0, which is the here which is the first order differential equation with constant coefficient. Here R and C are constants. Now we know that for differential equation it will give two uh, solution, one complementary and particular. So here the CD plus 1 by R is a characteristic equation, which is 0, which will give us the complementary solution, and from which we can get the transient response. Okay, so now D equals to minus 1 by RC. Thus this is a complementary solution from which we can get thus transient response or complementary part of the solution for the circuit. Transient response, let us say that arbitrary constant C1 e to the power minus T by RC. This is the response of the circuit. Now we have to find the arbitrary constant. At t equals 0, initial voltage across capacitor is VO, DC value. So VT equals 0 is VO equals, which is obviously this, which is C1 e to the power 0, obviously. So arbitrary constant C1 is VO. Thus the solution is, thus solution Vt equals initial voltage Vo e to the power minus T by Rc. This is the complementary solution for the RC source free circuit or transient response of the circuit. Okay, and for the particular integral part is in an electrical system a source is present, only then we can get a particular solution. So as there's no source in the RC circuit for this case, in this system, particular integral is 0. So thus complete response is, in time domain, complete response is this: Vt equals to initial voltage e to the power minus T by Rc. Okay, for frequency domain analysis, we have to transform the circuit elements or circuit parameters in complex S domain or frequency domain. So as this is a linear system, we can apply Laplace transform, and by Laplace transform the circuit uh, is transformed. As R is independent of frequency, there is no change in R. This always be R. And as capacitor is frequency dependent, it will be transformed after Laplace transform, and vice versa will give the capacitance itself in time domain. So capacitor with initial voltage after Laplace transform will be this, which is VO by S, and this will be 1 by SC. Or this is the voltage analogy. We can also use the current analogy. If we use current analogy, this will be, for current analogy, this will be this. This is the case, and we will use the current analogy in this for convenience. So this is linear circuit. Obviously this is obviously linear circuit, and we can use KVL KCL. We will use KCL. So by KCL at, this is node A, this becomes node A. Here we get IR plus IC equals CVO. We know that VO is equal to voltage, initial voltage. Now, which is from which we can get Vs by R plus Vs 1 by Sc equal to CVO, which will give us Sc plus 1 by R Vs, which will which is equal to VO. Now by rearranging, we get CVO by S plus 1 by RC into C. We can cut this. The C vanishes, which gives VO by S plus 1 by RC. By inverse Laplace transform, it will give Vt equals Vo e to the power minus T by Rc, which is the same solution we found in time domain analysis. Now the response of the RC source free circuit in both time domain and frequency domain is the same, and in the time domain analysis, the solution is by analyzing the circuit, we found a response voltage across capacitor Vt, or which is the response of the circuit, is initial voltage e to the power minus T by Rc, which is in time domain. And in frequency domain, in a frequency domain analysis, the solution is the same. Vt equals to Vo, this is Vo e to the power minus T by Rc. So that's it for today. This is the circuit analysis for source free RC circuit, which also gives the response of the circuit. We analyzed this circuit and got the response of the circuit. The response comes in action when we are emphasizing on the output of the of certain part of a electrical system. Okay, but we are what we're doing is we are analyzing different parts as a whole of the circuit as a whole. We are considering everything, and after consideration and careful assumption and approximation, we are getting a desired output. Okay, that's the response. So this is as a result of circuit analysis, we got the uh, time domain and frequency domain response. That's it for today. If you have any question or any problem in understanding, tell me in the comment section. And if you like my explanation, like the video and subscribe to my channel, support me. And thank you for today. In the next video, I will talk about step response, or what happens when a DC voltage is applied to RC or RL circuit.